All right. Hey, good morning, almost afternoon. Thanks for coming in for this talk. I understand it is prime 11:30 a.m. lunch hour. So thank you for enjoying this nourishment of my talk on security research with the Chrome DevTools Protocol. I'm going to jump right into it, do a little storytelling, and then walk through a couple of different interactive code samples and things like that. So if you do have your laptop, you might want to have it open, but it's not really necessary. I'm going to basically switch between slides and a little bit of code and a little bit of running stuff. And then you won't miss anything. I've got a GitHub repository at the end and a couple of other links to dig into and look at things. So with that, let's get started. First, I want to call back to an event that happened in June of this year. There's an article out there. Some cyber researchers responded to a report of unusual online behavior from an enterprise executive. So in this case, we're going to go to track through just like the security researcher in this example to try to understand what happened and what the impacts are for this organization, but also across the internet. In this instance, this executive, they are looking at his web traffic and they're like, okay, cool, what's going on? They see that our target, this exec, loads up this URL. And believe it or not, this is a benign URL. This is a real online Saudi Arabian website, and there's obviously WordPress, and there's some cached content here. No big deal. I look at this, I'm like, yeah, this is just more bundled JavaScript junk. But as you might expect, within this bundle is a reference to jQuery migrate 341, so another JavaScript dependency. And then within that bundle, there is just one line of obfuscated code appended to the end of it. All right, well, now we're interested, right? We're visiting this benign site. We trust this. What's going on? When we look at the evidence from this scenario, we say, okay, network traffic looks legit. I see a legit URL that I trust. I'm not worried about it. The file name itself, I'm like, cool, I'm not going to lose my mind over some jQuery plugin. This is some compatibility file. That's fine. And it's not going to throw up any issues in our code analysis tools, right? If I do an npm install for jQuery migrate, if it's coming from a legit source, cool, I'm not worried about it. If I've got my supply chain detection set up to look for this tool, I'm like, okay, cool, this is here, blah, blah, blah. It matches our static analysis. Maybe it doesn't. And that's how we see it when that hash doesn't match from the file content. But the point is, in this example attack, the one thing we see is that at runtime, we go to this page, there's actually a fake payment form being injected and exfiltrating data from the checkout page on the shopping website. Let's dig into it. In this real-world supply chain attack, the attack vector is that the user is visiting a legit but compromised business website. So I want to point out, in that example, this is a now compromised platform. We know that, and we want to dig deeper into that. We know we've got this disguised payload, and then we also, I can tell you a little bit more, and there's a link to this article in these slides at the end of it. But the attack further is pretty tricky because in that payload, the way that it runs is depending on the environment of the target. So like in this case, the payload's loaded up in the exec's computer, and like depending on the rules of the adversary, it might go, okay, cool, I'm in my targets box. I'm going to drop the real payload now, because obviously security researchers like us, we're going to go in and load it up. These adversaries do not just want to drop their payload on all of our machines for us to research and then write a crappy blog post about. Like they kind of want to save that for their target. And that's what makes this really interesting, because security research in the web space is not always going to be consistent. And I just want to mention that to think about as I walk through some of the examples here. This pretty much summarizes everything I just said, but the three main points: static analysis can be difficult, network traffic can be deceptive, and the evidence is often circumstantial. And this one example I point out is just one of many and many. I had trouble choosing what I was going to use as my little introductory case, but whether it's the most recent, I don't know if you heard about the NPM supply chain attack a week or two ago. Somebody fishes for some credentials and just sticks a little obfuscated JavaScript at the end of some trusted packages. If that attack wasn't detected, I don't know, a little sidebar here. In this attack, what I think is hilarious is that this person went to all the effort to compromise some pretty high profile packages that exist in a lot of dependency chains just to put in like a crypto wallet drainer at the end of it. They made $0. They checked the account. No money came out of it, even though this is easily one of the most widespread NPM supply chain attacks that has happened. But the reason it works is because as long as you've got code in that package, people are trusting NPM. People are trusting their supply chain and going, cool, NPM install. it's not going to show up on NPM audit because they didn't know it was vulnerable until they did, and then they pull these packages down. So it's wild to me how much we are blindly just okay with bringing in dependencies. But as security researchers, it's awesome because we get a lot of cool things to dig into and try to understand about what's going on in the greater internet. So with everything being said there, I've talked about a few examples, things we can dig into. The solution for us as researchers is to just ask the browser what's going on. When we want to think about the evidence that we saw and ways that it might not be so reliable, I like to cut to the chase. Let's load up this sample, or let's load up this page, or load up this JavaScript bundle, and let's interrogate the browser and say, hey, what's going on? What's being loaded? What's the behavior? And then use that to further our analysis of the scenario. And again, discover things just like this on the internet at large. A quick aside, why I feel I'm remotely qualified to tell you about this. I work as a security researcher at a company called BitSides. We're one of the better cyber ratings companies out there. Think of it as like a credit score for your company's cybersecurity. And while that's pretty cool, the cooler thing is we run one of the largest internet scanning pieces of infrastructure out there today, and that is called Groma. Google it. BitSides Groma, there's a couple of blog posts. These folks at Grainoise did some analysis of different benign internet sensors. I'm honored to say we are considered benign. I think it's exciting. But you can also check out some of our CVE discovery data at Groma.io. This is not a sales pitch. I'm just pointing this out because what this data we have enables is a talk like this where we'll start with one isolated incident, but then think about it on the scale of the internet. And that is the coolest thing because built into our internet scanning platform is our Groma headless browser. So in addition to fingerprinting services, platforms, kind of like what Shodan does, we'll also go beyond and load up target pages by the million and capture everything going on in that page using things like the Chrome DevTools Protocol. So what is it, right? I keep referring to this Chrome DevTools Protocol. You probably heard of Protocol and Chrome DevTools, but this intersection is going to be pretty interesting, whether you've got in-depth technical experience or still new to basic Python programming or even basic web development. In a very simplified kind of 100-yard view of it, the Chrome DevTools Protocol is just an API to interact with the web browser. Obviously, you can fire it up, hit F11, and start clicking around and digging with things, and that's fine for a one-off thing. But if you want to automate this kind of analysis or dig in and grab every statement, every line, or some crazy complex JSON that represents the DOM tree, the Chrome DevTools Protocol is awesome for that. And if you've used automation tools like Playwright or Puppeteer, those are also built extensions of the Chrome DevTools Protocol. So if you've used those, you've used the Chrome DevTools Protocol. But we're going to go and just focus on the DevTools protocol because there's some really neat internal functions to the Chrome engine that we can use to do what I mentioned before, which is ask the browser questions about what's going on in the browser environment. So if that sounds good, do you folks have any questions about where I'm at this point? I'll have a little bit of time at the end too to take some questions. So let me just get my notes together here and I'll go on to the next section. Cool. Folks who are just coming in, you've not missed anything particularly important. I've just been rambling for about 10 minutes. So this is, we'll keep it moving. So the way the Chrome DevTools protocol works is it's got these domains. Think of the domain as the kinds of questions you can ask the browser about what's going on. This is 5 of some 20 or 30 domains in the Chrome DevTools protocol, but when you think about that analogy of the actual user interface in the browser, when you hit that F11 key, these are some of those tabs you'll see. Runtime represents pretty much, the console. The debugger represents that awesome debugging features within there. Network is the network tab. The DOM section is kind of similar to what you get when you do inspect element, and then you can traverse the DOM tree and ask questions about that. And then finally, the page is mostly functional for us when using the DevTools protocol. We'll bring up a browser session and then tell it where we want to go and what we want it to do. The way that the Chrome DevTools protocol works, again, super approachable, and what makes it really fun is once you set up that WebSocket connection between your headless browser and your Python script, you just ask questions through these commands and then get answers through events. I want to point out that in the command section, there's an ID for each command that you provide. That's so you can map that response back through the event. And sometimes the browser will be more verbose and give you additional events you didn't ask for, depending on what domain you enabled. So all those features I talked about before, when we're actually programming this and creating our research tools, you need to make sure to enable those different domains. So to kind of share this with you guys and sort of dive a little deeper, I put together a very simple demo environment. This is our secure shop. Very exciting. You'll notice I bring in that same jQuery migrate dependency, totally unmodified, right? Wink. And then also a JavaScript bundle that's included on the page that brings in some web request tools, Axios, what they called, and then some of the JavaScript to make the page interactive. So let me bring that up really quick. So yeah, here's a little secure shop. Very exciting. I can put in no info and it processes. But this gives you a sense of what a real page might look like with some interactivity and some things going on here. And like we called out before, if I go in and I start, making requests, you can see here that there's some interesting stuff going on. We see that it looks like we're hijacking form submission, exfiltrating data. I see an HTTP request to an attacker-controlled domain. Okay, this is obviously something's going on here. Let's use the Chrome DevTools Protocol to ask the browser what's happening. So the first thing we'll do is look at observing the anomalous behavior, right? We see what's going on in the console. Let's make sure we've got some concrete evidence that something's funny is happening here and try to isolate what's going on and even where it's happening. The first way we're going to do that is get this irrefutable proof that the browser environment has been altered and that sensitive data is being exfiltrated. We saw some console logs, but okay, I need a little bit more than that. What we're going to do is use the runtime evaluate Chrome DevTools Protocol command. This is the best one because this lets you go in and evaluate any JavaScript within the page's environment. So simple as this, I say, okay, hey, I want to go and say, give me the stringified version of the built-in fetch function. Now, I skipped over some details here, but the reason I'm choosing to look at the fetch function is because, like we saw, we made a request on the page and we see some other things going on there. So we're going to analyze this. I'll explain more once I get to the actual code demonstration too. From there, we're going to say, hey, tell me what the stringified version is of this built-in function. And then we're going to also say, listen for network events that occur after I ask for some information about this method. This is important too, because like I mentioned, if we think something's happening with the web request, we want to see what that data is fully transparently and then analyze that output. So let me go to our first demo here. So what I'm going to show you now, and forgive me, I know I hate to be the guy that gets on the demo and just starts showing you a bunch of little code, but trust me, it'll be helpful too when you go back to this at the end because you're so excited to look at the repository I put out. This common.py, what this is a quick wrapper that I wrote around the Chrome DevTools protocol. So all this is doing is launching Google Chrome for my environment. Gives us some helper functions to just say, hey, I just want to do this or I want to do that, or a little bit of message handling. Like I mentioned before, the Chrome DevTools protocol is just going to continue to give us stuff over the socket and also give us an easy way to ask for those commands. So you might recognize this format. I need to give it a command ID, the method, so domain.debugger or evaluate some JavaScript, whatever else. And I can also provide some additional parameters. Yeah, that's pretty much it. This is used to launch the browser. So just to give you some context so you don't think, wow, it's 10 lines of code to do Chrome DevTools protocol research. A little bit more to it. And just want to give that context. So in our first example, this phase one of our analysis, like I mentioned, we want to confirm that something's going on there and see if we can get some more information about it. So we enable some domains. We say, yeah, give me page, runtime, and network. We'll navigate to the page, wait for it to load, and then we're going to make our first check. I talked a little bit about this in the description of this talk, but the concept of monkey patching is pretty straightforward. The browser comes with a number of built-in functions, right? You can go in and say, hey, I want to fetch this, or console log this, or error out on this. Those are native built into the Chrome's V8 runtime environment. But the beauty or curse of JavaScript, depending on how you look at it, is that you can go in and overwrite these behaviors pretty easily, especially as a talented security researcher like ourselves. And the way that is often used is test instrumentation, if you've got some big complex JavaScript project, or if you need to introduce some custom behavior into the tools and platforms that you're using. There's legitimate reasons to do this. Adversaries love to do it too because they can just grab something off the shelf, wrap it, make sure the fetch still works so no one thinks anything, and then also add a little exfiltration or do some other malicious behavior within the environment. So keeping that in mind, what's really neat about the Chrome environment is that if we're asking for actual stringified versions of these built-in features, in this case, I'm using fetch, you can ask for, hey, give me the string version of this. And if it's native code, that function output will say native code because that's what it is. It's native Chrome-based C++ code. And so if we ask for the stringified version of this, what we're going to get back is something that'll tell us whether or not fetch has been tampered with. I know it seems kind of like I'm just sort of understanding the problem right from the get-go, but again, we selected fetch because of the behavior we saw on the page. If you were doing this at scale, something to think about is you could just take every signature every built-in function of Chrome and just ask the page, hey, has this been modified? Hey, has this been modified? Hey, has this been modified? And then you have an understanding of, oh, okay, something weird is going on. Is it on purpose? Is it not? You can look at it from there. The next piece that we're going to do is once we understand that fetch has been compromised, we will also then use this script to understand where the information on the page is going. You saw there was a form there, and then once we hit submit, we should see our form data go out to our destination. Well, in this case, we'll inject a tracking marker. It's literally just a string, just a number that I'm aware of and control. And we're going to ask the browser, hey, where is this string going? Where are you seeing it? What is happening? And what can we do with that? And so less digging through code. A lot of this is just boilerplate I wrote around it to make the demo go smoother. So let me bring up the code here and go from there. So this is cool. We're launching a headless Chrome browser in the background. It comes up, loads the page. Great. Now we've run that analysis that I just pointed out. The first thing is that we can tell it's been monkey patched. When I ask for the function signature, I don't see the fetch code. I see function, fetch has been hijacked, and then there's some more attacker code built in there. Great. Now we know that it does not contain native code, and we know something weird is going on. Next, we'll inject the value that I control, this is not a real credit card number, obviously. Go try it out if you'd like. We find the form on the page, put the value into the form, submit it, and then listen in on the network domain to say, okay, cool. Do I see the value I'm looking for? In this case, we do, and we actually see it go as a post request to the attacker controlled domain. Great. We know the problem. We know that something's there. We know what it's doing. Let's keep going. This is the same set of slides. I put this in here so when you download my slides later and you're super excited to read about it again, you understand what I was showing you. Now, part two. Let's actually find where this modification is happening. Right? I've said it about 16 times. We see something's there. We see it's doing something. Let's go a step further. Actually, let me get back here. So we saw fetch was tampered with. Now, this is probably my favorite feature of the Chrome DevTools protocol. And again, there's so much you can do with this. In this case, we're going to use runtime evaluate again, and we're going to say, hey, Chrome DevTools protocol, can you just evaluate window.fetch for me? Basically run it without any input. Sure, we can do that. But I'm also going to ask the DevTools protocol, hey, don't give me the value. Actually, when I say return by value false, this is going to return an object ID. It's going to say to the browser, hey, how do you know what this function is? What is it in your memory? Cool. This is the handle to that function. And then immediately after, I'm going to say to the browser, awesome. Well, now I've got to handle the function the way you know what it is. I'm going to ask you for the properties and say runtime get properties with the function ID. And of the many things you can do with this, the one we're going to focus on is this internal metadata that the browser has called the function location. And that function location will be the exact source file that this function originated from. And then it's also its location within the file. You can imagine this is great because you can go to a page and say, okay, cool. It says they've got jQuery right here and it must come from this file. Well, let's ask the browser, where did it get this jQuery from? And you'd be surprised how many times you think you're using this version or this dependency, but really it's coming in from some third-party script you don't control. Maybe it's an ad services platform you've injected on the page, one of those annoying, dumb chatbots that brings its own jQuery on there. As long as you've got the content security policy configured that you can access all of those resources within your page because you trust them, you don't always fully have the control you think you do about what is happening in that browser environment. So I'll go to the demo now and show off this next piece. It's probably my favorite part. Pretty short here. Again, we're going to enable the same domains, navigate to the page. Then we're going to collect all of these script parsed events. So I didn't really allude to this well in the slides, but another awesome feature is we can load up the debugger and say, hey, forget just parsing all of the network information that comes in when you load the page. Instead, I want to keep track of every script that the browser parses when I load the page. So this tells me not just brought in as a resource, but I want to make sure that Chrome saw this and took note of functions and where they go and what's going on here. And this is really neat because you'll see a lot of things being loaded, not just network-based, but actual scripts that are calling in other scripts either from within the environment or outside of the environment. And then gives us something to ask questions about. And that's what I want to focus on. Again, thinking about the context of this talk, the security research is all about asking questions. And it's a lot easier to ask the browser a bunch of questions than it is to ask the developer if you can't get in touch with them. So we'll load up the scripts on the page. We're going to create a map of those script IDs that I talked about to the resources. And then we'll go a step further and we'll say, hey, window.fetch, where you at? Give me my object ID, and then use those script IDs we just mapped to say, okay, cool, this is where that object is. This is the location. So let me go ahead and run this next bit here. I guess I can make this bigger. So just like we expected, we actually see some of Chrome's own internal scripts being loaded. You know, when you go to any page, there's little interactive bits in Chrome and Chromium and other Chrome-based browsers. But the most interesting part is our dependencies being loaded here. So you see we load up jQuery from the jQuery CDN, and then we've got some of our local scripts that we've been digging into. Most interestingly, the old jQuery migrate, we think. So window.fetch, we grab that reference, we ask for the ID, and we're able to use the DevTools protocol to say, hey, yep, window.fetch did not come from the browser environment. It came from jQuery migrate. That's really weird. But even more interesting, I can go in and say, okay, cool, where's this happening? Let me go to line 4, column 23 of the file and actually see what's going on. Now, in this example, it's pretty contrived because, as you can see, I just put it there at the bottom, totally in plain text. But imagine this is seriously obfuscated, right? You don't even see the word fetch in there. You're not just going to control F through the source code to find this. Yeah, you could deobfuscate and do all that, but now you've sunk 30 minutes into the problem. And if you're doing this at scale like we are at BitSite, you don't have time to sit down and look at every page and debug the behavior one-on-one or one by one. We want to debug that behavior automatically at scale and generate information about what's going on the pages that we're visiting. So moving right along, discovered where it came from. Awesome. We don't trust that file. Now for the third phase of this is a very short piece of the demo, but just wanted to expose another really cool thing that you can think about when considering real adversary behavior out in the Wild West of JavaScript compromised dependencies. And in this case, let's pretend that our attacker has some kind of C2, right? In the initial example I gave, we are saying, hey, the adversary is actually going to reach out to its malware as a service and bring in the right payload depending on environment context. A lot of the ways adversaries are doing that now is forget doing it in traditional HTTP requests. Let's open up a WebSocket and hide the traffic there so that the more beginner researchers, not us in the room, of course, don't even think to look at the WebSocket traffic and what payloads are being brought in there. So in the same way that we've used the debugger network domains to ask the browser, hey, tell me what's going on when things are loaded, we can also ask it to look at what WebSockets are created and what the individual frames that are being sent and received are. Pretty similar to that first phase, just in a different context. So I will go back and show you that as well. It's pretty much what you expect. Navigate to the page. We've got the network domain enabled. We'll say, hey, let me know what WebSockets are created. Let me know what's sent. And then let's intercept anything that comes through. In this example, I got to be honest with you, I did not take the time to run a WebSocket server. So we'll just see the actual request go out to create the WebSocket. And even then, that's enough. You can imagine that maybe the WebSocket server that the adversary is running is offline right now, right? We don't even want the researcher to think that things are up and running. Launch headless Chrome, load in these events, say, okay, cool, yeah, I see a WebSocket connection. And you get a connection ID, which guess what? You can ask questions about that to the browser. It gives you something to trace down and understand what's going on. Here we say, okay, yeah, no activity detected as expected, whatever. But what's neat too is you might have noticed as well that this reference here isn't even in the jQuery migrate. Here we're exfiltrating using the built-in Axios instance, but in this case we don't even see where that C2 is happening. And that's because I actually bundled that behavior into the app.js. And you can see this is a messy JavaScript bundle, and I believe this one also gets obfuscated. But through the same line of reasoning that I just showed you in the first two phases, we can go find these kind of arbitrary events the same way, asking questions to the environment based on object IDs. So yeah, let's focus back on the scaling problem. You've seen something that you can sit down and do as a researcher. Those phases are just a couple of really simple tools I built, but it's just based on the Chrome DevTools protocol. Once you understand that ask and receive relationship, there's so much you can do. And I want to think a little bit, just kind of ideate with you here about going beyond these isolated incidents and doing research into this. Forget just looking and saying, okay, cool, this is what happened on my server. Now I know what's going on. I'd like you to consider this. Let's say we use the Chrome DevTools protocol to visit 100 pages. We know what we're looking for. We know we want to see certain behaviors for window.fetch. We know we want to see certain behaviors for console.log. What if we capture the expected behaviors, create a signature of that, and then visit every single page using these tools and just grab everything we can about what's going on and compare those signatures? It does two things. One, helps us threat hunt much more quickly. If we've got a sample of something a bad guy's doing, we can look for that bad guy behavior across the internet in different packages, in different payloads, and surface those a lot more quickly than you might otherwise by hand. The other thing is we can use that to actually understand better what the supply chain looks like across the internet. A lot of times, if you're an organization, you don't want these automated internet scanners going looking for your jQuery 1.11, right? All these CVEs in it. Folks will sometimes just take the jQuery version string and just remove it. No version. Cool. That fools like half of the simple scanners out there. They don't see a version. They're like, I don't know what this is. Next. And they don't even think to assign CVEs to that because the hash won't match, the version won't match. How do you know what it is? Well, yeah, you could do syntax tree matching, right? Where you generate a tree of all the behaviors you expect to see and then generate a tree of what you see on the target page. But again, complexity and time, those are both going to be increased with this behavior versus taking advantage of the Chrome DevTools protocol. If I'm already going to the length of loading up the page in a headless browser, this is all happening in the background already. So I can grab that information and keep moving on, especially like that script parsed event I showed you. Really interesting stuff you can dig into there. Another thing that I think is interesting beyond like supply chain, it's really interesting because we can ask those specific questions about what's going on. And when I think about the most recent NPM compromise, you can ask questions of what's like the blast radius of a compromise. Let's say that package didn't go detected. Cool. We can go further and actually try to understand that with our internet scanning platforms. Obviously, I'm going to guess not everybody in the room has the time, effort, interest, or resources to scan the whole internet at scale, but some of you might be thinking about your own internal tools, websites, your blog site, whatever. An easy way to apply this is just write your own scanning tool for your own environment. Generate signatures of what you expect to see. If you know that checkout page JavaScript is supposed to call in these dependencies and make these requests, and you see it doing something different, that's basic anomaly detection grown by yourself. Congratulations. So that's pretty much the final takeaway here. The browser sees everything, and with the Chrome DevTools protocol, so can you. Definitely check out some of the other domains here. The documentation is pretty well done, and there's a lot of cool demos out there. I'm going to pull up my notes really quick to make sure there wasn't anything really important I wanted to say. But with that, the final thing I have for you is, one, you can go to my github.com/TimTheGuy. The most recent repo there is those demos that I just showed you. So if you're interested in that, cool. Yes, I committed this morning. Sometimes I do things last minute. But if you're up for a challenge, I've also got a couple of small prizes throughout the rest of the day. If you're like me and you cannot commit time to a full CTF, but you want to like be able to say you won something, I've got this little mock scenario set up. And if you go to timtheguy.github.io, you'll see I've got this little analytics feed tool, pretty interesting. And if we go inspect what's going on here, see, okay, a payload is being attached to our log entries. Check it out. Fire up some of the samples I wrote for the DevTools protocol. There is a payload that is generated in memory. The payload is just a flag, but you won't be able to control F through the source for this. It's super obfuscated by me, and you won't be able to find that string the normal way. And if you do just want to run this through some deobfuscation tools, go crazy. But the first 3 people to send me a message on Discord, it's Tim the Guy. I've got a couple of ESP32 little mini boards with a built-in display that are pretty fun to tinker with, and I've got a bunch of stickers to give out too. So I'll be around all day. Send me a note if you want to try the challenge. Otherwise, I will leave this page up. That repo has the code. The bottom one is the little challenge, and I will put the slides in that repo too as well, because I realized I lied about sharing them. They're not out there yet. But I think I just blew through this in a good 30 minutes. So it's 15 minutes to ask me questions or go get lunch. Otherwise, thank you guys for being a captive audience. I really appreciate it.